Hey, Mr. Younger.
Hey Nathan, I see you in your car. I'm sorry about that, buddy.
That's okay. I was out on a trail run, and I used to be able to run that same trail a lot faster than I did today. So, uh,
Yeah,
but
yeah, that changes things, don't it?
my gosh, yes, yes. Yeah. Getting older
Well,
kind of sucks.
are you going to be able to do it, or do you want me to just schedule it later? The reason why I tried to push it a little earlier is we've been in our vets all day with the dog, and I have to leave with my wife right about 6:45, so that's why I tried to
Oh,
push it early.
I I only have like a couple conceptual questions,
Okay.
and the other ones I can just like email to you because I don't want to take up too much of your time.
That's cool. Go
Uh,
ahead and bring them up to me. And you can email them too if you need. That's not a problem. But yeah, I can help you as much as I can right now. No big deal.
okay. So like chapter 16 when we were talking about like electric fields and whatnot, and
Right.
then chapter 17 we're talking about voltage, and I don't have my notes right in front of me. I was trying to bring it up on my phone, but my notes
Oh,
taking a long time, so I'm kind of drawing on memory here. But the one, like, the main equation for it was force in the force of an electric field, K times
right,
Q over R squared, was
right.
like kind of the main one we were going to in chapter 16. And then chapter 17 had, I think, was it a similar one for voltage where it was K times,
The only difference is just like the electric field, there's only one charge on top, and the difference being instead of it being R squared in the bottom, it's just R in the bottom.
I didn't understand why it's just R.
That comes from remember me showing you how to calculate work, where
The,
work is F times D times cosine theta. But I told you if the force could actually change as the object is moved, like if the force was a function of position, for instance, then you
okay,
have to do some calculus.
okay,
That's what's going on. You actually have to do calculus to get from the electric field or the force equation, whichever one you use. And it turns out when you do what we call the integral, which is a calculus operation, if you do the integral of a 1 over r squared, you get a 1 over r. And
okay,
that's exactly where it comes from. And
okay.
it's a scalar too. So that's the other thing that makes it a really big difference is the V formula is just treated like a positive or negative number, and that's it.
And we didn't have to use any trig really when we're adding up multiple.
Yeah, you don't have to find components. The only times you use trig is maybe to figure out how far the two things are apart, because they'll give you a left-right distance and an up-down distance when the distance is actually diagonal. So you'd have
Okay.
to use Pythagorean theorem or something like that to find out the distance.
Um, okay. One of my other lab mate, Clarita, just
Uh-huh.
texted and asked if she could get in on this Zoom meeting.
Yeah, absolutely.
All right. I'll just,
Yeah, forward that email to her.
yeah, I will. Give me 1 second here.
That might
Uh,
help you too, because she might have some of the similar questions that you did that you can't access right now. And if you
yeah.
send it to me by email, I'll reply to them anyways, or text message, either one.
Okay. Yeah, I'm sorry.
No, that's no problem. It's my fault for trying to get you to come early when you were out doing something. That's,
uh, you're good. Let me see. And let me give her that link to. Oops. Are your dogs okay?
yeah, he got up this morning and he had thrown up some blood, and I'm thinking it's like a stomach ulcer or something, but he's a puppy. He's only 14 months.
Mm,
But we've been there all day. We still don't know what's going on, but they were worried because he hadn't eaten since last night and he still had food in his stomach.
gotcha.
So that's a little concerning, as you know from your EMT experience.
Absolutely. Absolutely. Yeah. I had a similar situation with my dog. Um, just recently, where she was couldn't keep anything down. The vet said it might be like acid indigestion because she's 12 years old.
Right.
But a lot of x-rays and blood tests and stuff for the vet to say, well, she thinks it's possibly acid indigestion. And okay.
Yeah, that's not cool. I have that problem, so I imagine it really stinks for a dog. I can't tell you. You imagine having a real bad heartburn and being a puppy or a dog. That sucks.
That would be horrible. That'd be absolutely horrible. All right, I just texted that information to Clarita and
No problem.
now.
Did you see the video I made last weekend? Because that might help you with the force equation. I've got another one I was planning on doing possibly tomorrow that will help with the electric field part. And then, of course, in class, I actually computed the voltage for that same sort of situation.
Right. I have to go back and like review my notes from class. I'm still like grinding my way through like all the reading.
Right. Yeah.
And I did not see those videos, but I will look out for.
It is on the YouTube channel, and it's called. Actually, let me look at it real quick, so I just let you know what you're looking for when you get there. Well,
okay.
It's called Solving Several Problems During Office Hours. That's what it is.
Okay.
So that's pretty straightforward.
Okay. Cool. I will look out for those. Kind of my other big conceptual question, like as far as the differences between 16 and 17, was the like in 16, is it like using the negative signs? We really didn't have to worry about the negative signs.
Yeah, you ignore them mostly and decide from the understanding of the equation and the way it works, you decide which way the force points in the case of the electric field or the force itself. And that's how you implement signs. Whereas the voltage, you have to absolutely use the signs in there so you'll know whether the voltage is positive or negative and that sort of thing.
Is that traces back to the fact that like electric field and force are both vector related?
Exactly.
And then the other one was the voltage is scalar.
Yep.
Okay.
Yeah.
Okay.
Hey, Clarita, see ya. You're welcome to ask a question at any point. I asked poor Nathan to come a little early because I need to run to the vet with my wife, and I stuck the poor guy out in the middle of nowhere without his notes or anything. So,
oh, good.
Time accommodating me.
Yeah, no problem. I had a question about one of the like example problems for chapter 16.
Okay.
I wasn't really sure how to start it, but basically it says a particle of a charge with +2q is placed at the origin, and a particle of the charge of -q is placed on the x-axis at x equals 2a. And then it says, where can a third positive charge be placed so that the net electric force is 0?
Gotcha. So what you have to do is think. So you've got a positive charge at the origin. So you sort of picture that in space sitting in the origin, and then off to its right, or my right, which would be your left. So you'd put it over here, of course. You picture a negative charge, and then you think, okay, well, if I put a particle between that, and did it ask whether to put a particular charge, or just say where could you put a third charge period?
It says positive charge.
Okay, so if I put a positive charge between them, then the positive charge would be repelled by the one at the origin, and it would be attracted by the one that's over to the right. So both of those forces are acting in a way to push that new charge to the same direction. So you can't get 0 out of that. So you know you can't get between them.
Okay.
Then you say, okay, well, what if I tried it to the left of the origin? And you'd see, okay, well, that's the negative charge that, or excuse me, that's a positive charge that you're putting to the left of the origin, and it's close to a positive charge, which should repel it. So it's going to be pushed left, and further to the right of the origin is the other charge that's negative. That's going to pull it to the right. So those two can actually cancel out. And the fact that it's twice as big was, did you say the other one was negative 2q? Or was it negative 3q?
It was +2 and then just negative.
Oh,
So
the
neg
other was just negative. Okay, so so then left of the origin is not going to work either because the other charge is smaller and the distance is bigger. So there's no way you can make it equate
Okay.
to cancel each other out. So that means you got to put it on the right-hand side of the rightmost charge. Can you
Okay.
picture that? You,
Yeah.
Nathan, both for that matter?
Yeah, that one tripped me up too quite a bit for a while.
Yeah,
Um,
then it's just a matter of you can either do it with the electric field or you can do it with the force. Doesn't really matter. But the main thing is, uh, actually, I guess with that one, you should, since the two things are causing it, as a bare minimum, you would use the electric field, and you could find out where to the right of the rightmost charge would the electric field be 0. So you just say, and in this case, since they're both along the x-axis, the vector quantity of the stuff is just expressed by it being a positive or a negative. And the positive or negative doesn't indicate what the sign is, except for the fact that it's a negative sign or a positive sign tells you whether a positive charge would be attracted to it or repelled from it.
Okay.
And usually with that kind of problem, you have to solve a quadratic equation using the quadratic formula or something like that. You might not even have to in this case.
So would I set the equation to 0?
Yes.
Okay.
I have my iPad. Would you like me to show you how I do it?
Yeah.
Okay. Let me go ahead and pull that out. I got it out now. I'm going to share the screen with you. And if you can remind me what the charges were and the distances, that would be great.
Okay.
Okay, this should pop up on your screen in a second. Okay.
Okay, yeah, I see it.
Yep.
So
So
I'm going to picture the
yeah.
coordinate system like this. And the charge was 2q at the origin, right?
Yes.
Okay, so that's a positive 2q. And then a distance 2a away
Yes.
was just a negative charge.
Yes.
So like negative q.
Mm-hmm.
Okay. And what we want to do is put a third charge, let's say somewhere here, and let's call this distance just plain x. And that charge is going to be, you say that one was a negative charge as well, or is that one a positive charge?
A positive charge.
Okay. So this one's going to be a positive charge. Did it say Q specifically or?
It just says where can a third positive charge be placed?
Okay. When it said plus 2Q and minus Q, were they both the same Q symbols or do they have like different
Yeah,
Q?
they were
Okay.
the same.
So I'm not sure that I'm allowed to call this little q, so I'm going to put a big Q just in case I don't understand the problem. Is that what you said that as example? Is that did they use a lowercase q in other words?
Yeah, they use a lowercase q for the 2q and just the negative q, but it
Okay.
didn't say whether or not to use one for like the third charge.
Yeah, but they didn't tell you that way, or you said it was an example in the book, right?
It was an example of like the chapter 16 practice on Canvas.
Oh, okay, gotcha. Okay, so yeah, what we could do is we could say the electric field at X due to let's say 2Q is equal to K times 2Q over X squared. We could say the electric field at X due to negative Q is equal to, now in this case, notice the 2Q would tend to push at the point down there that I said X is X distance away. If I put a positive charge there, which is what we're trying to do, the electric field established by the 2Q charge would actually tend to push that charge away because it's two positive charges. So I'm going to put a positive on there, and I put it there explicitly to show you that it's pointing to the right.
Okay.
Now, the one at that position due to the negative charge is actually going to compel it to move to the left. So I'm going to explicitly write a negative there.
Okay.
And notice I'm not putting in the signs of the charges. I'm just doing this to find the direction of the force. So that one's going to be K times Q. And in this case, it's X minus 2A would be the distance, and it'd be squared.
Okay.
Okay.
Yeah,
Now,
I got it.
what matters here is, since we're doing the electric field, I don't need to know anything about that charge. All I know is if I just put the electric field to be set equal to 0 at that particular spot, it'll automatically work out, no
Okay.
matter what charge I have. So now I'll say E total, which equals E at X, is equal to, notice we have a common factor of KQ, so I'll just pull that out from the very beginning. If that algebra bothers you, let me know, and I'll show you exactly the steps. But because I pulled out the K and the Q, all that's left for the E at X due to 2 is just 2 over X squared. And all that's left for the other one is minus 1 over X minus 2A quantity squared. Does that make sense what I just did there?
Yeah.
You get that too, Nathan?
Yeah.
So really the only thing that matters is what's in that parentheses has to equal 0. So I'm going to have 2 over X squared. Since they're both equal to 0, I'm going to go ahead and pull 1 over X minus 2A squared. I'll pull that to the other side. And now I'm going to cross multiply, because when you have two proportions equal to each other, or two ratios equal to each other, then you cross multiply and set the results equal to one another.
Okay.
So what's going to happen for the bottom right times the top left is going to be 2, and I'm going to explicitly write X minus 2A times X minus 2A, because otherwise you might forget to FOIL it. Remember the X minus 2A squared. So if you forget to FOIL it, everything will be screwed up.
Okay.
The other part is actually really easy because it's just 1 times X squared. So all I have to do now is do this multiplication, which would be X squared minus 2AX minus 2AX again plus 4A squared. So I'm going to say 2 times X squared minus 4AX plus 4A squared is equal to X squared. Now I'm going to distribute that 2, and I'll get 2X squared minus 8AX. Trying to make sure you can see that's a 2. Minus 8AX plus 8A squared is equal to X squared. So I'll subtract X squared from both sides. And that makes it a little bit easier, because now I'll have X squared minus 8AX plus 8A squared is equal to 0. And the quadratic formula says that if you have A x squared plus B x plus C is equal to 0, then X is equal to negative B plus or minus the square root of b squared minus 4 times a times c, all that over 2a. So I just have to recognize that this guy well, excuse me, not that one. Actually, I'll just, that this guy right here, 1 is A, that this guy right here is B equals negative 8A, and that this right here is C is equal to 8A squared. So now I plug that into the quadratic formula. I get the negative of negative 8A would be positive 8A plus or minus the square root. Now I've got a square negative 8A. So that's going to become, that's going to become positive 64A. A squared, I should say. And then minus 4 times A, which in this case is 1, times C, which is 8A squared. All that divided by 2A, which is 2 times 1. So we get 8A plus or minus the square root. Now you can see when I distribute that 4 to hit the 8, it's going to be 64A squared minus 32A squared, because 4 times 8 is 32. So I'm going to get 32A squared. All this will be over 2. Of course, 32 is 2 times 16. So I can write this as 8A plus or minus the square root of 16 times the square root of 2 times the square root of A squared. And I just wrote it like that so you can easily see what cancels out. Because remember, if you multiply what's under those square roots, you should get what was under the square roots before. Do you see that you get 32A squared?
Yeah.
Okay, so that should make it a lot easier on us. Now we have 8A plus or minus, let's say, square root of 2 times 4A over 2. Now you can see it would be 8A over 2 plus or minus square root of 2 times 4A over 2. You can see that the 8 is 4 times 2, so that 2 cancels out with this one. And you can see that the 4 is 2 times 2, so that cancels out with this one. And now we get x is equal to 4A plus or minus square root, or 2 times the square root of 2 times A. So your answers are 4A plus x is equal to 4A plus 2 square root of 2 times A, or 4A minus 2 square root of 2 times A. Now you can see this one's negative. So we can't use that one already because there's no way we could actually put the place on the left-hand side of the origin and still get the two electric fields canceling out. So we can ignore this one. So the answer should be 4A plus 2 times the square root of 2A. You could also just call this A times 4 plus 2 root 2, which 4 plus 2 times 1.414. I happen to know that's the square root of 2. So 6.828. So that should be where the thing is, a distance of 6.828A.
Okay.
Does that make sense?
Yeah, that makes sense. Why again couldn't we put the plus charge on the left side though? Why did
Okay. So if I put a plus charge here, you'd see that the force from the 2Q would be this way.
Mhm.
And then you'd see, maybe actually you could have. I thought we had already covered that, but that might have been when I was thinking something was errant. We do have to put a positive charge, but yeah, if we put it there, we could get one. So it looks like you can. I'm going to put the other force now. If I put a positive charge right there, obviously it would be oh, I know why. It would be attracted to the negative charge. So
Mhm.
this one's from negative Q. But notice the charge on the 2Q is bigger and the distance is smaller. So there's no way that force could have the same magnitude as the other force just because the other one's got a smaller charge and a bigger distance.
Okay.
Has a smaller magnitude of charge and a larger R. And since E would be K Q over R squared, you can see there's no way I can make that big enough. So cannot cancel. Force due to positive 2Q.
I got a question.
Go for it.
That at the bottom,
Mm-hmm.
where we ignored the 4a minus 2 square root of 2 times a, because you said it's negative.
Uh-huh.
I don't know that 2 times the square root of, does that come out to be negative? I'm
Yeah, the reason why I knew it is the square root of 2 is what you have to multiply by the square root of 2 to get 2. So if I had squared that square root of 2, then it'd be 2 times 2, which is 4a, and that's just barely big enough to cancel out the 4a. So I knew that the square root of 2 is smaller than 2, so clearly it's got to be less than 4a. The square root of 2 is 1.414 is another way of
Oh,
talking.
we're looking. Okay, never mind.
You get that?
Yeah. Yeah.
Oh, wait a second. Hold on. 4a, that's a positive. No, that's still positive. That's acceptable.
Okay.
Nice catch. Good job.
Okay.
I was reading it as backwards. I don't know why I read it backwards, but I was in my brain, I was thinking it was 2 root 2 minus 4, but it's 4 minus 2 root 2. So it's definitely positive. So that's actually a fair one, in which case it would be 4 minus 2 root 2. That was a good question you asked. So that was 1.172. I'm going to put an X through that and say this answer is X is equal to 1.172. So that's one option. And it looks like it could, in principle, be another option, but you definitely need to check them. Well, this one I didn't really square. When you actually, raise one side of an equation to a power, that often can introduce solutions that you didn't have before, so you always have to check it. This is not one of those, but you should still just check it to make sure. But it does look like you should have 6.828a and 1.172a. I'd be curious to find out if it really was. I see 1.172a. Oh, okay. I see what they're saying. That's them trying to put, notice 1.172 would be somewhere in here. And then this one out here would be like I said, 6.828. So somewhere way out here would be 6.828 A. And in principle, we had worked out that there shouldn't be any way to put it between it.
Yeah.
And that's because the force due to the 2Q we clearly push to the right, and the force due to the negative Q would also push to the right. So yeah, we still have to eliminate that one. So it should only have one solution, and it should be that 6.828.
Okay.
Sorry about making that arithmetic error, but it seemed like, you know, one of those things where the clock was right twice, even though the battery was completely dead. So I got two right answers for all the wrong reasons.
When we do that quadratic equation, though,
Mhm.
is it a safe assumption that like only one of those possibilities is going to be right?
I will tell you that a lot of times in electricity and magnetism, I have found that that second solution is right too. But I would probably say maybe 50-50, but I suspect that's because specifically the times that it was, both of them are right, was chosen specifically for us to see that example. I
Oh,
suspect it doesn't happen too often, but they found out the ones that did.
gotcha. Gotcha.
Good job. Nice catching on the 4a minus 2 root 2.
Thank you. I had a question about the equation sheet. Like I started working on mine.
Mm-hmm.
Like I think you had mentioned something about like if I sent it to you or I showed it to you, it could possibly be approved to use
Yeah.
on the that was I reading you right on that?
Yeah. Yeah.
And like,
And I told the students in class, you might not have gotten there in time when I told them. I thought I told them after you, but I might not have. I told them that when you're going through chapter 16, any equation that has that left parenthesis and then 16 dash or 17 dash and then a number and then close parenthesis, any equation with that, I actually allow.
okay,
So if you just go through the main body of the text in the chapters that we covered and copy all of them that are numbered, you can put all those on an equation sheet and that'd be fine.
okay, okay. We're gonna be given the constants too, right? Like
Yeah,
K.
and if y'all ask me about a quadratic formula, I'll certainly give it to you. You don't have to waste any paper space for that.
Okay. All right. Uh, I don't really have any more questions. Clary, did you have some?
Um, yeah, I have like one more question.
No
It's
problem.
like another question from like the practice, but it's basically it has like a picture of like a box, like a square,
Mhm.
and there's like a negative Q charge at the top left, a positive Q charge at the bottom left, and a negative Q charge at the bottom right. And it says, and there's like there's a crisscross in the box, and it says
Right.
which arrows represents the direction of the net electric field at the center of the square.
Gotcha. So you had a positive Q. I just drew it on the page. You said a positive Q at the top left, negative Q at the bottom right, and then what
A
else?
positive Q at the bottom left.
Like that?
Yep.
Okay. And then it had a series of arrows like this, I suspect,
Uh-huh.
meaning which of these directions is the net force, or did you say the net electric field?
Net electric field.
Okay. So what you want to do is I'm going to give this one a red color. I'm going to give this one a blue color, and I'm going to give this one a black color. And what I'm going to do is draw the direction of the electric field caused by each.
Okay.
So for instance, the plus Q in the top left, that's blue.
Mhm.
If I put a charge at the center, which is where that dot is right there, then that would create a electric field pushing away because the electric field is defined to be the direction in which a positive charge would be compelled to move. So just due to the blue one, that's going to cause that arrow to be down and to the right.
Okay.
Now, if you look at the negative Q at the bottom right, that's a negative charge. So that's going to attract a positive charge to come down and to the right as well. So that's what would happen due to the negative charge. Okay. And then the plus Q on the bottom left, that would actually compel a positive charge to move this way. And they want to know what is the direction of the total force, or excuse me, the total electric field at the center, right?
Mhm.
And this is the only four choices they have?
Yeah.
And you do say I have the positive Q is supposed to be at the top left corner. The
Oh,
positive.
wait, that's supposed to be negative. Sorry. The top
Oh,
left is
okay.
negative.
Okay, that makes more sense. Okay, so the top left's supposed to be negative.
Yeah. And then, yeah.
Okay, that's okay. I'm glad you caught me because I was like, that's not going to work. Ah. So now I'm going to get rid of this. And now I can put this back with that arrow. Okay, so that makes a lot more sense because now you said this one's going to be a negative Q.
Mm-hmm.
So since it's a negative Q, we now have a force that points this way for that guy. And you see they're equal in magnitude, the charges are, and they're opposite in direction, and their distances away from the dot in the center are the same. So the R is the same. So the red force and the blue force cancel each other out, and you're just left with the black force, which is up and to the right.
Okay.
That's
Okay.
the right answer, is that one.
So because electric fields go from positive to negative, you just have to look at them and like if it's a negative Q, the arrow is going to be pointing towards it because it goes from positive to negative. But if it's a
Exactly.
positive Q, the arrow is going away.
Yeah, I would not say the word because it goes from. I would just say a positive charge moves towards a negative charge, so the electric field points towards a negative charge, and positive charge is compelled to run away from a positive charge, which is why it points the other way. I just don't
Okay.
want you thinking there has to be another charge that it's running from to make it feel that force.
Okay. Gotcha.
The reason here was red and blue canceled one another. Does that make sense to you and Nathan?
Yes.
Okay. Yeah, these are good questions when they have those little diagrams like that, and they're asking you which direction is the total force and which direction is the total electric field. That gives you a good understanding. So remember the rule, and this is something you should probably write in sentence form somewhere if you don't already have it committed to memory. The electric field points in the direction that a positive charge would be compelled to move. And whatever words you want to do with that. I mean, I don't know that you use words like compelled or anything weird like that, but just whatever words you want.
Okay.
And you nailed it. It's, you know, if you're at a point in space near a negative charge, then the electric field points towards it. If you're at a point in space near a positive charge, then the electric field points away from it.
Okay. Gotcha. All right, that was it for me.
That's it.
Oh,
Anything else?
yeah, I'm good.
Okay, so here's those formulas just to remind you. We had the force was K, Q1, Q2. Nathan asked about this earlier, so I just want to refresh his memory. The electric field is K, Q over R squared, and then the voltage is K, Q over R, and this guy's a vector. This guy's a vector, and this is a scalar. Use the signs. Don't use sign. Don't use signs. And when I'm saying that, I'm not saying you're not using the signs at all. You're just not plugging them in. You have to use the signs to decide their direction. But other than that, you're good to go.
Okay.
Does that make sense to you there, Nathan, as well?
Yes.
Okay. Anything else?
I don't think so. Thank
Nathan,
you.
you were so accommodating. Feel free to go ahead and text me photographs of those problems you might have had when you get back home. Clarita, if you have any, that's not a problem either. Y'all can text me or email me, whichever one's easier for you. If you send it to my text, it's more likely I'll get it immediately and I'll answer it as quickly as I can, other than running to the vet, pick up my boy.
Okay.
So what the ballpark, when did you say we might be having the online test?
I would say it's definitely not going to be at least until next week or the week after.
Next week. Okay.
Yeah,
Okay.
at the earliest would be next week, and I'm sort of leaning towards the week after possibly. And
Okay.
it's going to be online, so a lot of times what happens is I'll make it available. Oh, and I say next week. I didn't mean this coming Monday or this coming Tuesday or Thursday. I meant the week after. Sorry.
Okay. Gotcha.
It's kind of fun watching y'all get scared. I'm like, yeah, not really. I'm playing with you guys.
Yeah, we have different ideas of what fun is.
Yeah. One person's comedy is another person's tragedy. Anything else?
No, thank you so much.
All
Thank
right. Well,
you.
do check out that video I put on there. Like I said, it's called Solving Problems in Office Hours or something on my YouTube channel. And that works. It shows you a really robust problem of working with vectors with the force equation of Coulomb's law. Okay.
Sounds good.
All right. Have a good one. Send me any questions you might have. I appreciate it.
Thank you.
Thank
You're
you.
welcome. Bye, everybody.
Bye-bye.